Welcome back to Beyond the Patterns. So today I have the great pleasure to announce two researchers. We have Supro and who is a postdoc and also associate researcher at the ETH AI Center, as well as the University of Zürich. And we have Chinmay Prabhakar, who is a PhD candidate also at the University of Zürich with Björn Menze, and an associate researcher as well at the ETH AI Center. Both of them are very much interested in, of course, deep learning on the one side, but also graphs. And in particular, they have discovered a new method how they can generate graphs and apply that to 3D vascular structures. So this is really a very, very cool approach because it somehow brings together the continuous way of diffusion models as well as the symbolic representation that you have in graphs. So the presentation is entitled 3D vessel graph generation using denoising diffusion. And without further ado, Chinmay, Supro, the stage is yours.
Thank you so much, Professor Meyer, for the very kind introduction. And we are more than happy to be here presenting our work to your group. As already mentioned, we are here to present the paper 3D vessel graph generation using denoising diffusion. This is a joint work with Dr. Supro and, who is also present in the call and would be more than happy to jump into discussions and take your questions. As for the brief outline of the talk, we would start with certain motivation and required background, followed by existing related work. Then look at our proposed solution and look at the efficacy of our solution by using two real-world datasets. So let's get started. We need to realize that the vascular graphs we are interested in are an example of a spatial or geometric graphs. Unlike normal graphs, which are set of nodes and a connection between these nodes represented using the adjacency matrix, a spatial graph is also embedded in 3D space. That implies each of the node has an associated 3D coordinate. Such spatial graphs are quite abundant and found near us. For example, proteins, molecules, or even road network supply or power supply graph. As already mentioned, in medical imaging, we see the spatial graphs in the form of vascular structures. On the left, we see the light sheet microscopic images and the associated vascular graph structure. And on the right, we see the human Circle of Willis, whose vascular structure can also be represented using a 3D spatial graph. Now, a question arises, why is it of central interest to start generating these synthetic graph structures? Turns out it is quite difficult to obtain a large corpus of such vascular graph structures. For one, the annotations is quite tedious, requires some special training, thereby making it expensive, or can even require some specialized tools in order to do the annotation process. Thus, obtaining a very large corpus is not trivial, and we often require large corpus to train any data-driven deep learning model. Thus, it is of interest to start generating synthetic vascular graphs that are very faithful to the underlying data distribution and can help us in handling this data scarcity issue. Let us see how the problem has been approached till now. Turns out most of the existing work tend to use a rule-based simulation where they take into account the oxygen concentration or nutrition distribution in order to generate such vascular graphs. These methods are mostly heuristic driven and struggle in capturing the complex topology. For example, the cyclical structure that are present in capillary beds would be very difficult to be captured by such rule-based heuristic methods. On the other hand, we attempt to solve this problem using a data-driven vascular graph generation approach. Our hypothesis is by being data-driven, we get rid of all the heuristics and let the model learn the underlying data distribution statistics and thereby learn all the complex topology. Since we want to go in the data-driven paradigm, there are multiple approaches that we could use. For example, generative adversarial networks, variational autoencoders, autoregressive modeling, or diffusion models. All of these have been used in the past to generate graphical structures. Turns out, as with the example of images, diffusion models have been very successful in graph generation as well. And they are currently state-of-the-art models for generation of graphical structures. Thus, in our approach, we also make use of these diffusion models in order to generate the vascular graphs. But vascular graphs pose certain unique challenges. For one, their data structure itself is rather unique. We have node locations, which are, as we said, embedded in 3D space, and thereby are continuous values. On the other hand, a graph connectivity, that is an edge between two nodes, by nature is a discrete structure. Thus, what we have is a combination of continuous and discrete components in the same spatial graph. To add to our woes, the nodes in case of vascular structures are rather uninformative. What do we mean by that? Let's take an example of another spatial graph which is studied quite extensively, molecular structure. In case of molecules, the individual nodes are atoms. As we know, for each of the atoms, we have certain well-defined properties, such as its atomic number, atomic weight, valency, etc. These properties can come very handy while trying to make a prediction about the connectivity between two atoms. On the other hand, for vascular structures, the nodes are actually bifurcation points, and as such do not have any of these highly expressive properties. Furthermore, sticking to the same example, we can imagine that a molecule can be oriented arbitrarily in space. Whereas for the case of vessels, we oftentimes have a preferred orientation, depending upon the acquisition protocol. Let's take the example of MR angiography or CT angiography images. Most of the times, the patients are either facing forward or facing down. It's very unlikely that we get these vascular structures in arbitrary orientations. Thus, as we can see, our modeling of synthetic vascular graph structures has certain unique challenges. How do we propose to handle these challenges? The central theme of our work is the realization that even though these vascular nodes, these bifurcation points in themselves are not very informative, but it turns out once we have fixed node locations, the node position themselves can act as a strong predictor to determine connectivity between two given nodes. And as such, we propose to use a two-stage diffusion model to synthetically generate vascular graphs. In the first stage, we learn the node locations. And in the second step, we fix the node location and then start learning the connectivity between the nodes. Let us take a look at each of these diffusion models in a bit more detail. Starting off with the first diffusion model, which tries to learn the node locations. At this point, we completely ignore the connectivity between the nodes, and what we have as an input are just normal point clouds. To these point clouds, we start adding random Gaussian noise, and then train a network to predict this noise. People familiar with diffusion literature would immediately realize that this is very similar to the DTPM formulation. It turns out we can use any other diffusion modeling formulation such as DTIM or even flow-based algorithms in order to train this first diffusion model. As a side note, for training our model, we make use of the noise prediction or epsilon prediction because we are sticking to the DTPM formulation in the given work. But as I already mentioned, we can use any other equivalent formulation to learn this diffusion model. Now for the second diffusion model, which learns the edge connectivity, things are a bit more tricky here. For one, the edges are discrete by nature, and hence it is suboptimal to start adding random Gaussian noise to them. Thus, we need to define a noising process which takes into account this discrete nature of the vascular connectivity. For this, we need to define the states, and as a noising process, we need to define a state transition matrix. People familiar with Markov chains can immediately see a relation here. As a concrete example, for us, the states would be the different edge types. I'm showing an example here where we consider 3 edge categories, namely thick vessels, medium-sized vessel, and thin vessels. But these categories are almost arbitrary, and our method can be extended to more fine-grained categorizations if needed. Sorry. What we see here as a transition matrix is an example of a noising process where, for instance, a given thick vessel in its noising step by application of this Markov transition matrix can either stay as a thick vessel, transform into medium-sized vessel, or even a thin vessel. Finally, the absence of an edge or the node deletion operation is also considered as a category. Thus, if we want to start noising the edge types, we can either change the edge type or completely delete it. And thus, we can obtain a noisy version of our input graph. To train a diffusion model, we have to take a closer look at the noising and the denoising process. If we talk about the noising and denoising process to train a diffusion model, there are 3 important things to consider. Number 1, this operation during training should be simulation-free, which means if we want to obtain the noisy state at an arbitrary time point t, then we need not run forward simulation t times, but this should be obtained from the starting position in, if possible, one-shot manner. Secondly, the limiting distribution should not depend on the original sample. Let us take the example of images again. As we know, for diffusion model, the forward process adds certain amount of noise, and eventually it turns into pure random Gaussian noise, and the original input image is completely lost. And finally, to train such a discrete diffusion model, we have to define what would be the training objective. In case of images again, we are usually making the epsilon prediction of the amount of added noise, and we need to see what would be the equivalent in case of these discrete structures. For the first part, that we want the forward process to be simulation-free, we can obtain it by considering the Markov property of these state transitions. Essentially, to obtain the noisy graph version at any time point t, we can just run the forward simulation k times by doing a multiplication of these transition matrices. To define the limiting distribution, which should not depend on the original sample, we make use of this specific transition matrix Qt as shown here. Let's take a closer look at this transition matrix. It has an initial parameter called alpha t, which is a monotonically decreasing function of time. At the final time point t, alpha t tends to become 0. And as such, we have just the right-hand side remaining. And if we take a look at the right-hand side, it just shows a uniform transition between different states. In other words, as is common with diffusion models, we are gradually adding more and more noises. such that with the transition becoming more and more tilting towards a uniform distribution as time progresses, and finally it becomes completely uniform transition between different states. As for the specific training objective, since our input is discrete in nature, it turns out that we can train our diffusion model by using a simple cross entropy loss between the clean graph predicted by our model and the original ground truth graph. Let us see this pictorially to be so that it adds more clarity to the operation. On the left, we have our original clean graph version. We sample an arbitrary time point t. Then we start noising this graph. The noising operation happens on the edges, and it may so happen that a given edge can either change its category or can completely delete itself. With this operation, we would get a noisy version of the original clean graph as shown here. Our neural network will take this noisy version of the graph and will try to predict a clean graph from it. We can train this neural network by using a simple cross entropy loss between the predicted output and the actual ground truth. In our case, we realized that we can add another node degree regularization term so that on an average, the generated vessels by our model match the node degree distribution statistics of the underlying graphs. The first loss term is the simple cross entropy loss, and the second loss term tends to encourage the model to align the node degree distribution closely. How does the sampling operation look? Well, the sampling operation is rather intuitive. We start with random Gaussian noise and use our first diffusion model to learn the fixed position of these point clouds. Once the point cloud positions are fixed, we use our second discrete denoising diffusion model, which tries to learn the edge connectivity. And thus, with these two stages, we can generate synthetic vascular graph structures. As a quick summary of our method, we propose to learn the node locations first, and following it, learn the connectivity between the nodes. The given GIF here tries to show the same operation with a 2D projection. As you can see, the node locations did not change. What we did was to modify the edge connectivity between the nodes. Since our method is completely data-driven, it is capable of capturing complex underlying topology, which was one of the main objectives of using a data-driven approach. Furthermore, to take into account vessel-specific characteristics, we make two important design choices. For one, because the orientation is not arbitrary, we turn off the rotation equivariance in these models. Usually, spatial graph generation literature always encourages to use rotation equivariant architectures, but in our case, we turn the rotation equivariance off. Furthermore, we also propose to use a node degree distribution regularization such that the model is able to better capture the underlying graph distribution structures. Let us take a quick look at our obtained results. To obtain the efficacy of our proposed method, we compare the resulting graph distribution with the actual underlying vascular graphs on various parameters, including the positions of the node, the degree of the nodes, number of edges, length of the edges, angle between the edges, to ensure that our model is not generating vessels which are at implausible, which has edges which are implausibly oriented. We even consider the orientation with the coordinate axis and take into account Betti 0 and Betti 1 errors. Betty 0 would take a look at the number of connected components, whereas Betty 1 captures the number of cycles that are present. Since this is a KL divergence loss comparison, the lower the value, the better. We compare our method on two real-world datasets. The first one is the VESAP dataset, which consists of light sheet microscopic images and the vascular structures derived from them. The second one is a Circle of Willis dataset, which takes a look at the human arterial structures at the Circle of Willis. As can be seen, our method quite faithfully captures the underlying data distribution, thereby showing the efficacy of the proposed solution across both these datasets. Here is a look at some of the qualitative examples. On the right, we have actual ground truth samples from the two different datasets. In the middle, we have certain samples that are generated by our method. And on the left, we have the samples that are generated by the best existing method before us. So our baseline methods, essentially. As we can see, the baseline method kind of struggles when the underlying topology becomes quite complex, and it generates implausible connectivity between the nodes. Compared to that, our diffusion-based generative model tends to generate more plausible structures, and thus is more faithful to the underlying graph structures. Since we are making certain vessel-specific design choices, we also run ablation experiments to see how much the individual components are useful. In essence, there are three things that we ablate against. The first one is in order to take into account the preferred orientation, we turn off the rotation equivariance. Secondly, to make use of the node positions as a predictor for the edge connectivity, we use the two-stage solution. And finally, to match the degree statistics better, we propose to use the degree loss. As we can see, each of the individual components, once added to our modeling paradigm, has a positive overall effect on learning the underlying vascular structure distribution. Finally, as a downstream application of these vessels, we train a vessel labeler. On the synthetically generated vascular graphs. A vessel labeler essentially takes a binary vascular graph as an input and tries to assign to it multi-class labels. These labels are derived from the TopCow 2024 MACI challenge. All the different from the TopCow MACI 2024 challenge, which consists of 12 distinct labels for the inputs. This vessel labeler is graph neural network based model, but we are free to choose different modeling paradigms here. In our case, we used something very simple because we just wanted to see how inclusion of more synthetic samples is affecting the model performance. So we have a vessel graph labeler, which is a graph neural network based shallow model trained using only the synthetically generated samples. It takes as an input a binary vascular graph, and then as an output, it tries to assign multi-class labels to this binary vascular graph. Please bear in mind that this vessel labeler is trained using only the samples that we generated using our diffusion model. To check the efficacy of such a labeler, we submitted this method as a baseline method in the TopCow 24 challenge. And without doing any specific hyperparameter tuning or using more complicated choice for the vessel labeler, we obtain quite decent results. Thereby, it shows that indeed our proposed method is able to generate samples that are quite closely matching the underlying data distribution. And such generated samples can also be used for different downstream tasks. This brings me to the end of the presentation. So in conclusion, what we propose here is a first diffusion-based generative modeling paradigm for vascular graphs, which is completely data-driven and thus is capable of producing complex topological structures. We make sure to adapt certain inductive biases which are specific to vascular structures and check whether the inclusion of these inductive biases have a positive effect on the overall learning. And finally, as we can see, we have certain promising initial results, which is an encouragement to us and shows that it is indeed possible to come up with a completely data-driven approach, devoid of heuristics, to learn these complex topological vascular graph structures. Thank you so much for your patience, and we are very happy to take your questions. Thank you.
Thank you very much for the presentation. This was very nice, very insightful, and I think it's a really cool idea to how to adopt a diffusion kind of paradigm to graphs. So this is really, really neat. I have a few questions. So you show how the QT is changing over the diffusion process. And just to be sure that I got all the details right, when you the states that you have there, so this is essentially for every edge pair that you're considering the same kind of statistic, or do you do that for the entire graph?
No. So this is a very good point. In our case, we are noising each of the edges independently.
Yeah. Okay.
Because if we start, there are some recent works which are trying to explore the idea of noising the entire graph together. But in general, if we start noising the entire graph at one go, the state space becomes quite large.
Okay.
Whereas for the independently noising and denoising of edges, the problem remains more tractable.
And if you look to the update equation, if I interpret that right, essentially you have a random state transition in the alpha equals to 0 case, and for alpha 1 you just stay in the same state. Yes. So
Yes.
Don't change anymore.
Yes.
Right?
So this is quite similar to when we look at the diffusion process for images. The idea is when the alpha is very close to 1, which means we are very close to the actual data, we are adding very little amount of noise. Whereas as we gradually go further and further, the amount of noise in the sample has increased a lot. And if we take the analogy here, when we are very close to our data distribution, when the alpha is close to 1, then we kind of remain in the same state and no noising is happening. But as we gradually increase the time period, the transitions can become more and more random in some sense, more and more towards a uniform distribution over the edges.
And when you're now doing the inversion, do you have a specific architecture and for doing that? And what are the inputs to this step? That would, because it seems, although you do it edge by edge, it seems you are able to use the absolute position of the nodes in order to determine where a connectivity is likely or not. So I wonder whether this also goes into your like denoising step.
Yes, that's absolutely correct. So for our denoising process, the network gets 3 inputs: the actual time point, as is common with all the diffusion models, the fixed node coordinates. So we are not changing the node coordinates at all. So it remains to be x0, or the clean version of the node coordinates. And then what we get is a noisy version of the adjacency matrix, this E of t here.
Okay.
And
but so the denoising is running on the entire graph structure at the same time.
Yes.
Got it. So there's a difference in the like noising step and then the denoising step. Okay.
Yes.
This is So in your results, you introduced like 3 classes of vessel thicknesses, and I'm not entirely sure if I saw that correctly. Is that the color coding that you have in your figures, or
yes. Sorry.
how do you the thickness?
True. Just a second. Let me just go. Yes. So we have 2 different data sets. The first one is the light sheet microscopic VESAP dataset, where we decide to use 3 classes of, because they do not come up with predefined edge categories. So we decide to discretize them into 3 categories: thick vessels, medium-sized vessels, and thin vessels. On the other hand, the Circle of Willis dataset, which is obtained from the Top Cow Challenge, actually has 12 edge categories. 13 edge categories, which are uniquely labeled by the annotators. So in the second case, we have edge categories predefined, whereas in the first case, we defined the edge categories kind of ourselves based on the vessel thickness.
And for the Circle of Willis, are you using this property that each category is unique by like a kind of thresholding when you assign them, or do you just take the top score?
Sorry, I did not fully get the question.
When you do the diffusion, then you assign essentially a state in which the vessels are classified, or the connections are classified.
Mm-hmm.
Now, you can, of course, just take the maximum likelihood for each individual one. Or you could also, because you know that there's only one, you could essentially choose the maximum of all of the vessels for the class assignment. Are you using that, or do you get these cool results even without implementing this extra trick?
So Supro, can you chip in?
Yeah, I kind of understand. So I think right now there is no extra kind of criteria to check all the edges of which is predicting, let's say, some kind of artery, and then only take the one which is the highest score. So we do not have anything, but I think it makes sense, because when we check the sampling stage, all these kind of vessel sample, like 10,000 sample vessels, we can see that in many cases there is implausible graft. So this problem is not completely gone.
But you're also the challenge organizer, so basically don't want your baseline system to outperform everybody else. So I can understand that. No, it's really it's super nice. So now that you assign essentially classes to each of these edges, and then you end up essentially with discrete thicknesses. So technically, you could also do discrete hidden states and then assign a continuous model, like a Gaussian mixture or a Gaussian for the actual thickness. Did you think about that anyway, or is that something you're planning to do, or because you want to get a more symbolic representation anyway, you don't think that the additional continuous thickness gives a lot of benefit?
I think it's modeling is okay, but I think predicting in the architecture, we are discussing the same thing over the course, to kind of have not just discrete edge properties, but some real valued edge properties, and how to model it in some way to have it consistent with having edge and not having edge, at the same time having some real valued property. And I think Chinmay can explain, like we ran into some problem that we kind of abandoned that idea. I think this Congress method that is in one of the baseline has some continuous version of the discrete factorizations, how they model the noising process, but I'm not sure whether they use hidden Markov process for it.
As Supro already mentioned, trying to incorporate these continuous attributes is something that is of a lot of interest to us. And at least in this initial version, we did not explore the part further of converting these discrete outputs into the continuous ones again. As for the method, I think we can think of, as you rightly pointed out, things such as Gaussian mixture model to assign these continuous attributes. But to keep the modeling very simple, we just, for the time being, stuck with the discrete nature.
I don't think you're stuck. So I think you're doing fundamental research here, and it's very natural to extend in this way. And of course, you do the fair step first. Yeah? So that's no critique. It's really cool. So I liked using hidden Markov models. So I've been doing speech recognition for quite some time. And there are all kinds of different discrete, continuous, semi-continuous HMMs and so on pop up. And there's also interesting ways of how to map that into neural network architectures and things like that. But sorry, this is just a personal interest of mine. I personally think stuff that you're doing is really, really cool. So I think it has many, many possible ways of extensions, and there's many works that can be done down the line. And yeah, I think it's super cool what you're doing.
Thank you. Thank you so much.
So this also brings us already to the end of our discussions, and I really want to thank you guys. This is super cool work, and I think this tackling symbolic nature and continuous nature, you're doing really, really good work into going into that direction and make it compatible with all the neural networks that we have now. And I think much more work like this should be done. So thank you very much for being here, and thank you for sharing all that great work.
Thank you.
Thank you, Professor Sander, for the invitations, and thank you for having us here. Very much like it.